Hello everyone. Thank you for your interest in our work, which explores the dynamics of colliding Bragg solitons in an optical coupler. I am Nadia Anam and I will be carrying out the rest of the presentation. What motivates us to perform this study is, first of all, we wanted to understand what happens to solitons when they collide. We wanted to demonstrate that if an identical pair of solitons are considered, their collision is quasi-elastic in nature. We explored if there is any dependency on phase angle of soliton collisions. We expect our results to indicate that solitons could be suitable for switching purposes. And finally, we wanted to create the scope for further analysis of collision under different conditions. Now, before I get into the specifics of our research, I would briefly like to discuss how moving Bragg solitons are created. We know that the periodic variation of refractive index within optical fibers give rise to structures which are known as fiber-Bragg gratings. The coupling effect that exists between the forward and backward propagating waves in FBG structures give rise to high levels of dispersion, which are much higher than the dispersion present in regular silica fibers. If we are able to counterbalance this high level of dispersion with a high enough nonlinearity, since nonlinearity is an effect which is pre-existing in optical fibers, then theoretically we would be able to obtain high intensity lossless pulses which are termed Bragg solitons. A lot of research has already been conducted on such solitons, and it has been suggested that they could be suitable for the design of novel optical devices. Hence, we are interested to explore Bragg solitons in different nonlinear structures, such as the one that we have used here, which is a semilinear optical coupler, and understand what happens to moving solitons when they interact with each other. The basics of our model are derived from Maxwell's coupled partial differential equations. We have developed them to represent our semilinear system with cubic-quintic nonlinearity in one core and a linear core with Bragg gratings. Here, U and V represent the forward and backward propagating waves in the nonlinear core, while their counterparts in the linear core are represented by phi and psi respectively. The cubic-quintic nonlinearity strength is represented with Q. C is the group velocity ratio in the linear core, and lambda is the coupling coefficient in the same core. The group velocity ratio in the nonlinear core has been set to 1. Because we are dealing with moving solitons, their normalized velocity is represented with sigma. Upon inspection of the linear spectrum of this system, we find that there are 3 band gaps in this model. The upper and lower band gaps are the only ones that have moving solitons in them, and they are of 2 different types with varying phase and parity. Only type 1 moving solitons were found to be stable, hence we consider them for the collision dynamics. We numerically solved the following pair of equations for the nonlinear core and the linear core respectively. Here, delta x represents the initial separation between the counterpropagating waves, and delta theta is their phase difference. Sigma plus and minus are used to indicate the direction of propagation. An example of in-phase soliton collisions is shown here with the respective parameters. We observe that as the counter-propagating solitons move, there comes a point when they seemingly merge and then pass through each other with negligible decrease in energy but increased velocity. Also, the separation is symmetric in nature. For a phase difference of pi, the counter-propagating solitons never really merge but rather bounce off each other. This time the velocity decreases, although the separation still remains symmetric. In conclusion, we can say that the interaction of an identical pair of solitons results in them either bouncing off or passing through each other. The post-collision outcomes of such solitons are indeed affected by the phase difference between them. The collisions in our model result in quasi-elastic behavior because the pre- and post-collision energy levels are almost constant. It is important to analyze the characteristics of colliding solitons because it helps us to further understand these low-light applications of solitons. I would like to thank you for your time, and if you have any further queries regarding our research, please feel free to communicate.